So what do we have? We have an ideal gas mixture. It consists of 40% nitrogen, 30% carbon dioxide, and 30% methane. It enters a well-insulated turbine. The temperature that it enters at is 1200 Kelvin, pressure 1500 kilopascal, with a given mass flow rate of 5 kilograms per second. It expands isentropically through the turbine to a pressure of 100 kilopascal. Determine the exit temperature, determine the power developed by the turbine, and the rate of entropy production. All right, so let's go ahead and make a sketch. Maybe we'll sketch a turbine characteristic, something like this. Inlet, outlet, state 1 on the inlet, state 2 on the outlet. The purpose of the turbine is to have a shaft, and it produces some power. So we talk about the mass flow rate coming in. That was given to be 5 kilograms per second. We're just organizing the information that's given us in the problem statement. Has a temperature coming in of 1200 Kelvin. Has a pressure coming in of 1500 kilopascal. And it goes out at a temperature T2 that we're asked to solve for. What is that exit temperature? So we don't know it. And it goes out at an exit pressure of 100 kilopascal. It's an ideal gas mixture, and ideal gas mixture consists of 3 components. Well, I need to really understand all the problem given in this problem statement. First of all, what is that 40%, 30%, 30%? You have 2 choices. It's either mass fractions or mole fractions. Typically, you have to make an assumption, or hopefully the problem is more clear. I would say this is mole fractions. Okay? Typically, it's more common to talk about the makeup on a molar basis. Okay. Also, it says it's well-insulated turbine. Maybe I put some hash marks indicating Q dot equal to 0. True? Is there any other information that's in this problem statement that I should grapple with? Okay, it's isentropic. So what does that mean? Does that mean, like isothermal would mean T2 is equal to T1, isobaric, P2 is equal to P1, isochoric, V2 is equal to V1, isentropic, S2 equal to S1, or did I not interpret that correctly? Is that the correct interpretation? It's the correct interpretation. Very good. So how am I going to solve for part A the exit temperature? Yes, sir.
Can I do the ideal gas equation of P
Oh.
over T and then
Yeah, so whenever you see this ideal gas mixture, we know that there's 3 things that come to mind. True? That's what you're reminding us of. So you're reminding us that PV is equal to RT. Is that true? And that U is a function of temperature only and that H is a function of temperature only. Is that true? All right. Is that what you're reminding us of? Or is it something else?
My question is, should I start with this equation to solve for T2 by putting P1 equal rho RT?
Okay. You're looking to try and get for T2 from this equation. That's typically what we call a dead end. And when you're solving problems for the first time, that's what the problem with faculty giving lectures that's limited to 50 minutes. I don't want to go down too many dead ends. So I avoid dead ends. But when I was a student struggling with new concepts and new problems, I went down some of the same dead ends you did. I still remember my statics class. What an eye-opener. Oh, I'd have one equation, 2 unknowns, and I'd struggle for 3 hours trying to solve it. Can you solve one equation with 2 unknowns? No matter how brilliant I was, I couldn't do it. So sometimes it's good to know, oh no, that's a dead end. Don't go there. Back up. Bend down that one. I know what it's like. It doesn't get us anywhere. No, using ideal gas equation to get T2 is not going to work by itself. So anybody else have another suggestion for how to get T2?
T2 equal P1, T2 equal T1, P2 over T1.
One of the good things you could do is you could say, let's do mass balance. Let's do energy balance. Let's do entropy balance. Let's do a first law. Let's do a second law analysis. See if it yields anything. Okay. Embedded, you could kind of see, well, isn't this already the results of our second law analysis? I know it is. Okay. But let's say, and mass balance, isn't that just saying mass flow rate in is equal to mass flow rate out is equal to mass flow rate? It's steady state. Where does it say it in the problem statement? Nowhere. But where do we have transient turbine problems anywhere in the textbook? So if it doesn't say it, that's a good, safe assumption. Say, I'm going to assume steady state flow through this. Where does it say anything about neglecting kinetic potential energy? It doesn't, but it's safe to assume it. I don't have any information given to try to account for elevation changes or speed changes of the flow in and out. So if we take a look and write the first law just for a clearly defined system, what do we pick up? I know we can do it in 2 or 3 steps, but that first law gives us something like the power out of the turbine, out that control volume, out that shaft, is equal to the mass flow rate times the enthalpy in minus the enthalpy exit. Have you done the first law enough for turbines that look good? Yes. But you've got to go back to the basic equation, apply it, manipulate, simplify, and get that with confidence. Okay, now, what about the second law? Well, let me try and draw the most elaborate second law equation. Rate of change of entropy in the control volume with respect to time. Hey, professor, you said there's no transient. I know. Is equal to the rate at which it's transferring in, bringing with that heat transfer the entropy transfer. Hey, professor, I thought we had a well-insulated turbine. What's Q dot?
0.
Thank you. Then it's bringing in with the mass flow rate coming in, it's entropy in. It's taking out with the mass flow rate, it's entropy out. And if there was any irreversibilities, you'd have entropy generation. True? They said it was isentropic. So what is the change in the S?
0.
What can I conclude about sigma dot? 0. So it's somewhat like... okay, it's a reversible, well-insulated turbine. Congratulations, it's isentropic expansion through the turbine. Okay, a little bit of a dead end, but not too bad. I want to get T2. How do I get T2? Basically, I recall a property for ideal gas, S2 minus S1 must be equal to 0. The change in entropy of the fluid, the ideal gas mixture flowing through the system must be equal to 0. And I know that I can get an analytic expression for the change in S of an ideal gas mixture. It is C sub P, natural log of T2 over T1 minus R, natural log P2 over P1. Do you agree?
Yes.
Does that equation look good?
Yes.
But how do I get this C sub P and R? I have to do a little work. Okay, let's do this. How do I get, let me set up a table. I'll say the table, I'll put the species or component. Let me put component. Component 1, 2, 3, what is it? It's nitrogen, it's carbon dioxide, it's methane, CH4. Now, can methane be an ideal gas? Yes, it can. But if you get it to really high temperatures, high pressures and low temperatures, it can also not behave as an ideal gas. It can behave as a real gas as well. Where a greater range of pressure and temperatures, nitrogen would behave with high accuracy as an ideal gas. Okay, so methane can behave as an ideal gas. What I want to do is I want to list the mole fractions that are given in this table, 40%, 30%, 30%. And then I want to kind of build this table out so I can eventually get these C sub, the specific heats in this gas constants. Okay, so I think about having, I pick where I have 1 kilomole of stuff of this mixture. If I had 1 kilomole total of this mixture, how many moles would I have of nitrogen? 0.4 kilomoles, 0.3 kilomoles of CO2, and 0.3 kilomoles of CH4. You see what I'm doing? I'm saying if I start with 1 kilomole of the mixture, I'll have 0.4, 0.3, and 0.3 kilomoles of each of those entities. Okay. Now, if I know the molar mass of each of these components, then I could get the mass that's in this 1 kilomole of the mixture. Okay, so I go out and I say, okay, for nitrogen, I'm reminded the molar mass is 28.01. For carbon dioxide, it's 44.01. And for methane, 16.04. Each of these have units of kilograms per kilomole. True? Is that true or not? So how do I get the mass in kilograms that I have? I started with 1 kilomole of mixture. How many kilograms of nitrogen are in that 1 kilomole of the mixture? Well, I just take and multiply the amount times the molar mass. True? And so that gives me a mass of the mixture that is 11.204 kilograms and 13.203 kilograms and 4.812 kilograms. So if I sum that up, I get the total mass of that mixture. That total mass is 29.219 kilograms. Now I'm doing this slowly because what is the mixture molar mass? What is numerically the mixture molar mass? Well, it's how many kilograms of mixture I would have per kilomole of the mixture. I started saying, let's focus on 1 kilomole of the mixture. And we concluded that that's how many kilograms there are in that 1 kilomole of mixture. So guess what the molar mass of this mixture is? The molar mass of the mixture is 29.219 kilograms per kilomole. First time you do it, it's like go slow, think through it, but that's the molar mass of the mixture. Yes, sir?
What tells me to assume that using a constant specific heat for this problem is for simplicity?
We don't have a table for methane. So even if we wanted to count for the variable specific heats of methane, we would be forced not to use a table. Okay. The second thing is this textbook does have an analytic expression for the specific heat as a function of temperature over a limited temperature range for methane. You can find that. If you have a textbook, I think it's in table A21. So you could do it that way. It's not a bad way to do it. I'm going to use that polynomial expression for the temperature-dependent specific heats of methane. It's in the table. I'm going to use that in a minute or two. But basically, I'm going to use that not to integrate the polynomial, but to simply evaluate that polynomial at one temperature, which is the average temperature, so that I can just use a constant specific heat evaluated at appropriate average temperature. But methane is the real challenge here. Yeah. Okay. Yes, sir.
Are we not able to use equation 6.43 where T2 over T1 is equal to P2 over P1, K minus 1 over K?
Yes, you can use that equation. But how do you get the K's? We're going to long rate. We're going to rederive that equation. But is K equal to 1.4? No. How am I going to get the K? We're doing it right now. But we'll get there, okay? You jumped ahead of me. You know where we're going, which is good. Anybody else? All right. So now I got the molar mass. Now what I do is I go and I look up just the specific heat at constant pressure, and I say to myself, okay, but is it a function of temperature? C sub P is a function of temperature, is it not? For nitrogen, for carbon dioxide, for methane? Okay. So what I said was, I need to get the C sub P of the mixture. And then I need to get R of the mixture. Okay? And then I can solve for this T2 in this expression right here. Because it's the only thing I don't know. I know T1, I know P1, I know P2. All right, so what I did was I said, let's guess what T2 is. And let's say the first guess I used a 1.4 for K, and I used the expression that was just described, that T2 is equal to T1 times P1 over P2 to the K minus 1 over K. But I don't know what K is. So I guess that it's 1.4. I put it in there, and I get a T2 that comes in at around, I forget the value. But then I take that T2, here, you run it. You run the calculator. You tell me what T2 is. You have a calculator? Right there is 1200. It's 1 over 15 to the 0.4 divided by 1.4. What do you get for that temperature? 553 point something. Okay. Now do this. Find the average temperature between T1 and T2. T1 comes in at 1200. T2 is 553. Find a good average temperature between those two. Just add them together and divide by 2, right? 877. So what I'm going to say is I'm going to use this T average to get the specific heats where the average is 877 Kelvin. Okay. Maybe you round that off. Maybe you round that off to 900 Kelvin. Okay. Are you sure that these numbers are correct? Who else ran this number? Anybody else run this number? What did you get? Did you get the same number he did? What was your T2 again?
500, 150 something.
553. 553. I'm going to look for about 3 confirmations on that number. You got 553? 554. Add 1200 to that and divide by 2. Add 1200 to that. 870? 876. Okay, it's in that vicinity. It's slightly below 900. So I go and I grab some specific heats at that temperature. Okay, I grabbed them thinking it's a little bit more than 900. I grabbed it at an average of 930 for these numbers if you want to reproduce it on your own. And now it's a chore. How did I get nitrogen at 930? I could have used the table. Great. I could have used a table for CO2. Great. Methane, I don't have a table. I was forced to use that polynomial expression that's in the table. Okay? That polynomial expression, alpha, beta, gamma, delta, epsilon, what I found was that the methane came in at a C sub P bar. Let me do the C sub P bar. It was 68.915. For the carbon dioxide, it came in at 53.38, and for the nitrogen it was 32.293. Okay, that's C sub P bar, isn't it?
That's using the 930.
Pardon?
That's using the 930.
That's using 930 for the temperature in that polynomial expression. And then if I multiply by or divide by, that's a good clicker question. C sub P bar, I'm given it. I want to either multiply by M or divide by M. Do I multiply by M to get C sub P, or do I divide by M to get C sub P? I'll turn on the response system and collect your responses. I just calculated CP bar. I want to get C sub P. Oh, you don't have time to look it up. You have to just tell me. Oh, you already voted? All right. Everybody vote? Yeah.
Would you mind to recall the polynomial for that?
I don't have it. I don't have an electronic image of it. Let me stop this and see where we're at. All right. So vast majority says we divide by. Look at the units. What are the units on? It's kilojoules per kilogram Kelvin. This was kilojoules per kilomole Kelvin. So if you divide by molar mass, which is kilograms per kilomole, the kilomoles cancel, and you're left with kilojoules per kilogram Kelvin. Congratulations to the 84% that had that correct. All right, so what we do is we then put a column of C sub P there, okay? And the units, how do I get that C sub P? I take the C sub P bar, divide by molar mass. All right, and so let me put in some numbers here. For nitrogen, the specific heat constant pressure was 1.153, and for the carbon dioxide 1.213, and for the methane 4.296. Now you can check these two numbers with the table. It looks great. You can also go out on the internet and check some tables for methane evaluate around 900 Kelvin. It'll look great too. Okay. But what I need is I need to get the specific heat of the mixture. How do I get the specific heat of the mixture? Yeah, so kind of tucked equation over here. C sub P of the mixture is the sum of the mass fractions times the specific heat of each of the components. So I need to get those mass fractions. Well, I have all the information to get the mass fractions. The mass fraction of nitrogen is this 11.204 divided by 29.219. True? Isn't that the mass fraction? Okay, so the mass fraction for the nitrogen comes in at 38.3%. The mass fraction of the carbon dioxide, 45.2%. And the mass fraction is 16.5% for the methane. So by mass, it's primarily carbon dioxide. By molar analysis, it's primarily nitrogen. Why the switch? Carbon dioxide is a big, heavy molecule. For each kilomole of CO2, there's a lot more mass. It's heavy, it's big. Okay. So then I do the product of the mass fraction times the specific heat. That intermediate calculation isn't all that important, but the sum of those three entities summed up, usually that's what we do in a table, we put the sum below, gives us 1.6977, which is the specific heat of the mixture. So I just calculated C sub P of the mixture, 1.6977. What about R? How do I get R of the mixture? R bar over M. That's the easiest way. Okay? So this R is just R bar divided by the molar mass of the mixture. Makes sense? Okay, so now I can solve for this. T2 is equal to T1 times P1 divided by P2 to the R divided by C sub P. Couple steps in algebra there. Somebody says, how does that compare with this? How does this, how does this compare? This with this. How does it compare? They sure do look alike. Are they the same? They're exactly the same. Okay? So R divided by C sub P is exactly equal to K minus 1 over K. And with a little algebra you can show it, but I'm running out of space here, so let me persist. So what I did was, once I have that, I update the value of temperature. So T2 comes in at a much different temperature because the the K is much different. The K actually, if you want to compute the K, I did the K and it comes in at 1.201, not 1.4. And if you do that, what you find is that the T2 comes in more like 762 Kelvin. You could do one iteration and call it quits. You could do a multiple iteration, do it again. Say, now I know the exit temperature is not that, I have a better estimate. I'll update the temperature of the average. So the updated average temperature is 980 Kelvin. Redo it. If you redo it, then you'll get a better estimate of the exit temperature, 769 Kelvin. So we're starting to work on that third significant digit. Well, don't worry about it. You're pretty good. You're close enough. One or two iterations, you're done. And so there is the exit temperature. Make sense? All right. How about the power developed by the turbine? Well, here was our equation right here. Isn't that the equation we already developed? Energy balance gave us the equation for the power. M dot's given, 5 kilograms per second. I need to get H1 and H2. How can I get those H's? Can I replace that by M dot times C sub P T1 minus T2? I will ask a clicker question. A, yes I can. B, no I cannot. Let's start this clicker question. Somebody says, I think you can calculate it by replacing delta H by C sub P delta T. So instead of M dot H1 minus H2, it's M dot C sub P T1 minus T2. Yes, you agree? Answer A. B, you say, no, not going to work. Answer B. All right, everybody in? Let's go ahead and stop. And we show the results. So it's true. Let me ask you this question, because some people would say, no, you cannot use C sub P because that process, the gas is undergoing, is not constant pressure. Is the gas undergoing a constant pressure process as it flows through the turbine? No. So somebody says, I think you cannot use that because C sub P, what is the definition of C? Specific heat, constant pressure. What's the P mean on it? Constant pressure. Do you remember the other variable, C sub V? What was the name at Allen? Specific heat at constant volume. True? And so specific heat at constant pressure. They say you can't use it because through the turbine it's dropping from high pressure to low pressure. So can you or can't you use it? You just voted yes you could. That's the correct answer. Now the answer is why? Can you defend it? Let me spend just a little bit of time helping you review this. What is C sub P defined as for all substances, whether they're liquids, whether they're gases, whether they're solids? Doesn't matter on the phase. What's it defined as? The rate of change of enthalpy with respect to temperature holding pressure constant. Is that true?
Yes.
Where did we learn that in this textbook? Way back, right? Early. All right. Now, we did learn something about an ideal gas, and that's what we're talking about right now. Ideal gas mixtures made up of ideal gases. So we said, oh, PV is equal to RT, always for an ideal gas. U is a function of temperature, always for an ideal gas. H is a function of temperature, always for an ideal gas. So when we bring this information over, what we find is that that partial derivative turns into a ordinary derivative. We use a different notation for that, and we don't have to say holding P constant because H is not a function of P. Is the enthalpy of an ideal gas a function of pressure? No. It's only a function of temperature. Whose experiment helped confirm that? Joule's experiment, one of his many experiments. He did a number of experiments, but this one is worth reviewing. Let me do a quick review of this experiment. He took a container, let's call it container A, and he had it connected via a valve that he could open and close to another container, container B. These are rigid containers. No matter what the pressure is inside, it didn't change size. All right. He then took and filled container A with some ideal gas. Well, what's a good ideal gas that he used? Maybe he used nitrogen. Maybe he used oxygen. Maybe he used argon. Maybe he used some other ideal gas. Okay. And then maybe he had the same gas in both sides, but he had them at different pressures. Maybe he even put one all the way to a vacuum. It's probably conceptually better to put it all the way to a vacuum. So you have all the gas in the system in tank A. Tank B is completely empty. What's the pressure in tank B? 0. What's the definition? What's the temperature? It's not defined. It's 0. It's not defined. The temperature is not defined in tank because there's nothing there. Okay. Then he put it into a big water bath. Okay. And this is all filled with water all the way around it. Good contact thermally with the box, and then the gas inside the boxes or the rigid tanks are in good thermal contact too. So if he ever heated up the water, eventually the gas would heat up. If he cooled down the water, gas would cool down. So he stuck a thermometer in there so he could measure. What do you measure with a thermometer? So he could always monitor the temperature of the water. And he didn't want it to heat up, and he didn't want it to cool down, so he insulated this tank very, very well. Very, 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 very well. Now, if he had it really well insulated, and he detected a change in the temperature of the water, what do you think he could conclude? But that there was a Q between the two tanks, A and B, with the water. Because there's no Q, and there's no boundary changing either. There's no work. If there was a change in the temperature of the water, it had to come about because there was a heat transfer between the gas and the water. Okay? It's a little step there in logic. All right, now, he had this filled with the ideal gas, this one empty. He had the valve closed. He then opened it. The gas moved. Now you have it well distributed between two sides, A and B, two tanks, right? Then he said to himself, did the pressure of the gas change in the tanks? Yeah, they changed. It went from high in A and nothing in B to mediocre or some average. Did the volume of the gas in the tanks change? Sure, it spread out. It was small and confined always on one side, but now it's spread out to both sides. Okay. But he looked very carefully at the temperature, and he saw that there was no change in temperature of the water. So he concluded there was no heat transfer between the water and the gas, and the gas was at the same temperature. So the temperature didn't change of the gas, even though the volume changed, even though the pressure changed of the gas. True? See that? Then he did this. He said, let's go and write the first law for a system that is this system. All right. Well, you could do it a couple ways. Let me do it this way. Do the system where it starts here and ends there. So the system actually expands into the empty tank. All right. Write the first law for that system. So you have the final internal energy minus the initial internal energy is equal to the heat transfer into the system during the process from 1 to 2 minus the work that the system does pushing back whatever from 1 to 2. But it didn't push back anything. It pushed into a vacuum. If it pushed into a vacuum, there's no work. We said there's no heat transfer between the water and the gas, because he detected no temperature change in the water, he concluded that's 0. So he concluded that U didn't change, even though P changed and V changed. So he said at most, it's not a function of pressure or temperature, it's only a function of temperature. Now to prove it's a function of temperature, that's real easy. All you have to do is put a little flame to it to pump some heat into it, and he could easily see that the temperature goes up as you add more heat. So it wasn't, but he ruled out that it was a function of pressure and temperature with this experiment. Thank you for listening in to a Cliff Notes version of Joule's experiment. But it's a big one because he concluded that U is a function of temperature only. You ever wonder why that's true? Professor, I'm interested in passing the class. Only take my level of knowledge to sufficient level to pass the class and be done with it. Now, once you have this, why is H a function of temperature only? Well, H is defined as U plus PV, true or false? And look what PV is equal to. RT. R is not a function of pressure, volume, or anything. It's not a function of temperature. R is the constant. T is a function of temperature. It's T. So basically, once you get that U is a function of T, H is a function of T, false. So what we do is, when you have this, what you want to do is you want to unravel that derivative. And if you have an interest in calculating the final enthalpy minus the initial enthalpy, it's the integral of C sub P dt. We don't like integrals as engineers. We like to make very simple. So when in doubt, use an average specific heat over that temperature range times the temperature range or temperature difference. Make sense? So go back to this. That's the correct approximation. We had the specific heat of the mixture. We had the two temperatures. You calculate the m dot. I'm going to erase right here, not the m dot. You calculate the power. W dot is equal to, and you get that the power is equal to 3730 kilowatts, good to 3 significant digits. Last question. The rate of entropy production. What symbol do we want to use for this answer for part C? Sigma dot. Now, I'm going to ask a clicker question. Sigma dot, do I expect it to be less than 0, meaning it's negative, equal to 0, or greater than 0? Answer A, B, or C. Let me go ahead and turn this on. So, sigma dot. I'm going to calculate sigma dot, the rate of entropy production. Do I think that it's going to be less than 0? Answer A. Equal to 0, answer B, or greater than 0, answer C. We're not quite to 100% correct. Should I give any more time? Here goes. Ready to stop? Stop we go. And let's show the results. So I know this is bad, but what did we do? We went over here to this equation. I forgot what equation was this one. The second law, and we struck a bunch of terms, and then we came and what did we conclude? That sigma dot all by itself is equal to 0. So congratulations to the 91%. Now, let's say I forgot that. Let's say I said I'm going to go and calculate sigma dot's equal to m dot times S2 minus S1. I encourage you to do that. And when you run it, maybe in your calculator, you're going to get a very small number close to 0. There will be some round off because maybe you didn't carry 7 digits on the temperature. Maybe you did. I did this problem in Excel, and it comes to 2 times 10 to the minus 15, letting Excel keep all the temperature digits and everything else. Okay? 2 times 10 to the minus 15 is engineering parlance for zero. Let me go ahead and stop here. Next time I'll start into psychrometrics. Thank you for your attention.